Hello, this is Bryant Myers, and welcome to another episode of Debunking Flat Earth. I'm going to be starting a new series called Debunking DITRH, or David Weiss, and this is going to be some fun. It's going to be similar to our series with Debunking Witzit's stuff from the last debate, but only we're going to also include DITRH in the mix here, and we're going to use, like the Witzit videos, we're going to show a little video clip, and we're going to come back and talk about it. And today's episode, we got one of DITRH's favorite topics is these really high speeds, of the Earth rotating at 1,000 miles an hour, the Earth going around the sun, etc. But I want you to hear it in his own words, and then we're gonna come back and talk about it here.
Spinning 1,000 miles an hour to the east. That's what they tell us.
And then then NASA says that the Earth is moving around the sun at how fast?
66,600 miles an hour. Funny number for a
company
that has a snake tongue. Somebody that has and we're chasing the sun. The sun is moving at over 500,000 miles per hour. So all of the planets, while they're spinning and orbiting, are chasing the sun in a third direction.
Whoa, really?
And to make it worse, the entire galaxy is moving sideways at like over 2 million miles per hour.
Really?
Nonsense. All nonsense.
Yeah, it sounds like nonsense, doesn't it, DITRH, if you don't understand science? But this is just an argument from incredulity. You just think it's so incredible that it just can't be possible. Not understanding what an inertial reference frame is and basic science and why these speeds are possible. So let's just kind of go through this. And I just want to start by just taking a look at his little animation, because this vortexing model that he shows is absolutely ridiculously inaccurate. I mean, it's about 1 billion times faster than it really is when you look at some of the like, say, Neptune going around as fast as it is in this image. So, and this is the problem, is flat earthers don't seem to understand the idea of scale and size and how this relates to how these fast speeds also have very slow rotations associated with them and very small forces. So we're going to really look at that in this video. And we're going to see that numbers matter, that math matters. Because if you don't use math, yes, it just seems so incredible you just can't put it all together. So I want to start with this idea of an inertial reference frame. There's many ways you can kind of define it, but it's an unaccelerated frame, or a frame that's going at constant velocity. And within this frame, Einstein showed that the laws of physics and all inertial reference frames are the same. And here's the thing, there's only relative velocity. We really can't measure, there's no measure of absolute velocity. And in fact, the human body can't detect velocity. When you're on a plane going at, even the old Concorde jets going at 1,300 miles per hour, if there was no turbulence, even going that speed, you wouldn't feel anything. And it turns out there is no instrument that measures constant velocity. Now, there are accelerometers. We can measure acceleration, a change in velocity, and we can also feel that, but we can't feel or detect constant velocity. Even the speedometer in your car is going by the rotation of the axis in your tires. So I like this little image of this bullet train going at 300 kilometers per hour, which is 170 miles per hour. And you can see, I got this from Simon Dan. I don't know where he got it from, but it's such a cool little clip. And you can see that there's really no forces here. You can balance things. And the thing about these trains, these bullet trains, is they have like a magnetic system, so there's not going to be as much bumps as typical trains. So it's a really great example of how you don't really feel constant velocity. In fact, as we'll see, the accelerations, besides gravity, the other accelerations on the Earth due to the rotation of the Earth are very, very small. And we'll see that the main rotating acceleration is the centrifugal acceleration, but this is very, very small, 0.03, as we'll see, meters per second squared. And there's been some studies done on the human sensitivity, and this acceleration due to the centrifugal force is so small that it's literally on the threshold of our ability to detect it, which is why our planet is very well approximated as an inertial system, because the rotating forces are so small. So I'm just kind of tired of seeing these flat earth memes where they have pictures of Australia upside down. So as I just mentioned, our body can detect through the vestibular system acceleration. So we can feel acceleration. Our body has the ability to feel it. And because the acceleration, like I said, is mainly gravity pointing down towards the center of the Earth, this gives us our sense of up and down. People that are in like a 0G type of chamber, they don't have any sense of up or down. So up or down is literally defined by our ability to feel acceleration and also kind of visually in how we see things fall as well. Okay, so now I want to get to why these really fast speeds lead to forces that are very, very small. And it has to do with, many things, but very visually it has to do with scale, and I'll talk about curvature here in a second. So here you can see, this is actually to scale now of our Earth. So when you zoom in on the Earth, because again, it's just a gigantic 3,950 mile radius, huge. But look now, we're zooming in now. This is Mount Everest. So just kind of take this in, just how huge and how vast our planet is. Just amazing. I mean, just absolutely mind-bogglingly large. And you can see here, it's like it is kind of locally flat. It does. I mean, it's hard to see the curvature. Okay, now related to the size and the scale, and we're going to see how this is important with curvature. When you have, again, the Earth is at the equator, it does have a tangential velocity of 1,000 miles per hour, roughly. So that does seem very fast, but again, we talked about how Concorde jets were going 1,300 miles an hour and people weren't feeling anything when there's no turbulence. So you can see from this little graphic on the right here that as the radius of curvature gets larger and larger and larger, you can see the curvature, which is the inverse, gets smaller and smaller and smaller, meaning it becomes more and more like a straight line. So as you have, and this is kind of a relativity component too, because we're very, very small relative to a very large sphere, and you can see that as the Earth is rotating, it does approximate very well, I mean, just moving in a straight line because it's so large. Now, it still is a curved path, but it's not like these sharp turns. It's sort of like when you're driving and you take a long banking turn, you don't feel it, right? But now if you take a sharp turn, of course you're going to feel that acceleration. It doesn't mean the acceleration was absent in the long gradual turn. It just means that the radius of curvature was so large that the acceleration was just very, very, very minuscule. So the same thing is going on with the Earth rotation here. So again, getting back to this vortex model, when it comes to the radius of curvature for the Earth around the Sun, it's even larger, so it's even more of a straight line. And the acceleration forces, as we'll see, are even smaller. And with the Sun around the galaxy, 500,000 miles an hour, but it's almost a perfectly straight line, relatively speaking, from our reference frame. I mean, the radius of curvature is so ridiculously large because our galaxy is so large that we're pretty much going in a straight line for all intents. This is why the acceleration, as we'll see, due to the galactic rotation, it's so minuscule that there's no instrument that could even detect it. Okay, so I want to bring in another clip here with DITRH, and this is important because I want you to listen to what he has to say when I kind of go through, because I just got kind of sick and tired of them saying that the Earth rotates at 100 miles an hour. No, it doesn't. The Earth, that angular velocity is measured in radians per second, or you could say RPMs. So the angular velocity is 0.000694 RPMs, or like 2 to the minus 7 radians per second. It's not 1,000 miles an hour. That's the tangential speed. Two totally different things, but let's just listen to them here a minute. The actual centrifugal force, you end up with 0.03 centrifugal acceleration, and this is a very small force.
But Brian, you're just reciting numbers and beliefs.
So I want you to really take this in, because flat earthers they're actually more anti-math than they are anti-science. I mean, because they do take in certain scientific principles. But it's not numbers and just beliefs. And this is what I want to kind of go through next here. All these numbers, and I like to again, I call this, fast speeds and slow rotations and small forces. Because when you put pencil to paper and do the calculations, and then you can measure these things in reality, the numbers do match reality. So this is not about, I mean, it is about numbers, but it's not about beliefs. What the flat earthers have are all about beliefs because they don't use numbers. And so they're just kind of saying, well, this is too incredible that things can go 1,000 miles an hour, therefore it's not true. Again, as I said, angular velocity is measured in radians per second or RPMs or cycles per second, not miles per hour. I mean, think of the engine in your car. It's not, it's measured in RPMs, not miles per hour. So it's just something that flat earthers need to correct. So the centrifugal acceleration formula you can see over here is basically a mega squared r. So we will go through that here, but you can use this formula and actually calculate the actual accelerations due to these different centrifugal forces. So for the Earth and the orbit around the Sun and the Sun orbiting the galaxy, we know these rotational speeds, and we know the radiuses. So we can actually calculate, which is what I did, all these different centrifugal accelerations. So it turns out that even though the Earth is going faster around the Sun than it's rotating, because again, I was telling you, when you actually do the calculations, it's actually the centrifugal acceleration is much less. But look at this. Around the galaxy, we're going even much, much less. It's just, the scales are just so large and the radius of curvature is so huge that it's almost just like traveling in a straight line. So for all practical purposes, we are an inertial system. And the laws of physics hold just fine on our planet because all of these, the faster the speeds go, you can see the smaller the forces because the radiuses get larger much more so than the speeds do. So again, you got to put pencil to paper to see this. And then we can actually then calculate these numbers. And as I've mentioned in other videos, geodesists and professionals can use gravimeters and can measure the gravitational force and gravitational acceleration. You can measure with accelerometer as well. And what's really cool is that you can use this equation here, use actual physics and science. This is not just beliefs. We're actually using scientific theories and laws that have a lot of evidence, and we can make the calculations and use gravimeters and accelerometers to verify our results. And this equation here is Helmholtz's equation. It basically allows you to calculate with pretty good accuracy the gravitational acceleration, which then relates to the gravitational force at your location where you're living. As long as it's at sea level. If you're at an altitude, you have to correct for altitude. So the first term here you can see is just 1, and that's just using the gravitational acceleration at the equator. So now as you go up in latitude or down in latitude, you're taking the sine squared because the tangential speed gets slower and slower and slower. So the centrifugal force due to rotation gets up to near 0 at the poles, and it's greatest at the equator. So this sine squared term is a correction term for your latitude. And this is why you'll weigh less at the equator than pretty much anywhere on Earth. And now this other term here, which you can see is much smaller, is correcting for other gravitational anomalies. And these are based on empirical numbers that geodesists will measure. Now another way, this is from Wolfe 6020. He measured, there's another way you can kind of, without having to get a gravimeter, is if you have a sensitive scale, you can see at different latitudes the weights change. And they will change based on the Helmholtz equation, as I just showed. But what the point is that you can kind of prove to yourself that the centrifugal force is real. These are not just numbers and beliefs, Dave. We can do the measurements and see that our numbers match reality. So what's going on here? This centrifugal force is basically right at the threshold of human detection. It's very, very weak. But yet, the tangential speed is 1,000 miles an hour. And this is, again, where the incredulity arguments come from flat earthers. So now this is Jaron, from Jaronism, going through, he's calling it edge speed. You know, they got their own little terminology for this stuff. So let's watch this little clip here.
You guys think they are.
What do you mean? 1,000 miles per hour is 1,000 miles per hour. That's the edge velocity.
No, it's not. Rotation is measured in radians per second.
Of course it is. But you can.
Okay.
But can you not figure out the edge velocity?
Okay, so again, they just think, like I mentioned already with the Concorde jet. I mean, you could get a picture of a Concorde jet over land, seeing how fast it's going, but you're on the jet itself and you're not feeling anything. They just don't seem to understand that there's no forces in a constant velocity, even if it's 500,000 miles an hour. And again, not understanding physics is not an argument against it. So you guys need to understand what an inertial reference frame is, and that constant velocities can't be felt, they can't be measured, to get a sense for just how weak 0.03 meters per second squared is as far as acceleration. You can actually use a standard size merry-go-round and basically to quantify it and make it precise, if the merry-go-round had about a 5-foot radius, which is 1.524 meters, and you timed it such that it took you 42 seconds to go once around. I mean, think about that. You're taking the merry-go-round and you're going around once every 42 seconds, okay? Now, if you put the numbers in to our equation, our w squared r, the acceleration comes out right at what the Earth's acceleration is. But this is an accurate depiction. If you're going to accurately talk about what the Earth's rotation would be like on kind of the smaller scale, just find a merry-go-round, or you can come up with other types of rotating systems too and do the math. But when you do the math with the right radius and the right period or the right angular velocity, you'll see that the acceleration is just hard to detect, just undetectable. So this is something I actually had a one-on-one little talk with Dave, and I wanted to try to explain to him kind of a deeper understanding of this balance between the centrifugal force and the gravitational force. Because it is true, when the radius is small, the centrifugal term does dominate more in these two-body problems. And you can do the two-body equation with you on the Earth because you're one body and the Earth is the other, and you're rotating on the Earth. But the center of mass is going to almost be exactly in the center of the Earth because the Earth is 6 sextillion tons, and you're just much less mass. So that's why you can kind of set this up and it works. But what's interesting is as you go out, as you get larger and larger radiuses, this is where the gravitational terms start to dominate. And the centrifugal force, which is again based on the angular speed or the angular velocity, and even related to the tangential velocity, has less and less and less of a bearing, which is why those accelerations around the solar system and the galaxy got less and less and less, because as r gets greater and greater and greater, that centrifugal force is just totally washed out. It's almost zero. And gravitational force is still there, though. So this is why, again, the water doesn't fly off the Earth, because it's the whole Earth is spinning. And again, it's twice as slow as the hour hand on your clock. So if you want to visually understand how fast the Earth is really rotating, again, the Earth rotates at 0.000694 RPMs, not 1,000 miles an hour. And you can, another way you can kind of show this is that the tangential speed at the poles is 0, roughly. So that 1,000 miles an hour is only at the equator. But the whole Earth, everywhere it's rotating with the same angular speed or the same angular velocity. Now, I want to kind of conclude this video here, again, to debunk DITRH, and just show, this is one of his favorite little demonstrations, the rock on the string. So I want you to hear it in his own words, and because I did this little experiment myself, actually just last night. So I want to come back and talk about where his reasoning is flawed. It's actually flawed in many ways.
So in your world, rim speed doesn't matter. It's only angular speed that matters. But in the real world, we can prove that rim speed is everything. A simple experiment you can do is if I had a rock hanging on a 2-foot string and I spun around, I'd have to spin around pretty damn fast to make it stick out. Yep. But if I spun around and I let out more and more line, got it out to 50, 100 feet, I don't have to spin that fast. I can spin slower and slower and slower, and that force is stronger and stronger the farther out. At the same time, I could hold a 2-foot string and the 50, 20, 100-foot string, whatever it is, and I could spin around. The 2-foot string would barely move out, even though it's going at the same angular speed. But the rim, the one way out there, the rim speed is much faster. It's actually pulling on my arms. Okay, so I hate to say this, but he actually was not incorrect when he talked about you do
and I did the little experiment last night, you do have to rotate faster when the radius is smaller. And as it goes out, you don't have to rotate as fast. But this is all based on the equations that we have. And when you actually do this rock on the string for the radius of the Earth, here's the thing, you have to idealize it to a massless string and no air resistance, which actually is a fair approximation because the Earth is rotating as a rigid body. It's rotating in space with no friction. But here's the problem, what he's doing. Here on Earth, and I drew a little, because again, Dave can't draw a free body diagram to save his life. I did a little free body diagram here, and the problem with DITRH's experiment is he's not realizing a couple things. Number one, again, he's trying to equate this with, taking the string out to the radius of the Earth is kind of where he's going as you get greater and greater and greater. And it does tug. I mean, if you are going at the same angular speed, you're going to have, again, omega squared r. If you've got the same angular speed, that's constant. The r keeps getting greater. You're going to have more and more of a centripetal force you're going to feel on the string. But here's where he's going wrong. He's not factoring in gravity, number one. He's not factoring in the weight of the string, number two. And he's not factoring in the drag force or air resistance, number three. And on top of all that, he's going way too fast. So here's the problem. The Earth, again, 0.00694 RPMs. That's twice as slow as the hour hand on your clock. So if you were trying to rotate a rock twice as slow as the hour hand on your clock, what's going to happen? The rock is just going to fall right to the ground, right? You can't, and I kind of figured it out last night. I kind of used a pail to a little more massive object. And I had to rotate about 10 to 20 RPMs to kind of get it going at a small, and then you can let the line out more and more and more. And it is interesting. Once you kind of let it out more and more and more, then you don't have to rotate as fast. True. But I was still rotating nowhere near 0.000694 RPMs. That's just, again, twice as slow as the hour hand on your clock. You can't rotate that slow here on Earth without gravity just pulling it down. And so this is why the free body diagram is important, because it will show you the minimum speed that you need to keep that rock from hitting the ground. And it's in the RPMs. Even when you let the line out further and further and further, it's nowhere near what the Earth's angular velocity is. And so, and the other thing is drag forces. So when Dave is feeling his arm get tugged more, even though he's slowing down and it's going out, and we've all seen this with flying kites, right? When you fly a kite, you can see the string starts to bend inward. So that's the air resistance. There's a force that's acting on the string, especially as it gets longer and longer and longer. This starts to compound more and more and more the further you let it out. The other thing is the mass of the string. So again, if we're going to try to make this analogy work with the radius of the Earth, that's a lot of string. Even if you're using a really thin string, 3,950 miles, that's a lot of inertia. So you got to calculate, the moment of inertia for that string. So can you see where Dave's experiment is flawed here? Definitely, if you haven't seen my video number 4, I go through flat Earth science, and I kind of made that spelled funny, but it's because flat earthers can't seem to draw a free body diagram and understand that there's more than one force acting on these objects. So this is fun. I don't have much more to say today, but I just hope that after watching these videos, when you hear these flat earthers talk about these fast speeds, you'll have a deeper understanding of how to calculate the actual forces, and that it's not rim speed that's the most important. What's the most important is the angular velocity. And when you really think about it, the Earth is rotating twice as slow as the hour hand on your clock. I can't emphasize this enough. And even though that slow rotation, because the Earth is so big, does give rise to a large tangential speed at the equator, because that speed is in a near approximate straight line, because the radius of curvature of the Earth is so large, this is why we don't feel that force. So it's, again, size and scale and curvature play into this too, along with the very slow rotation, which is why we don't feel these forces. And which is why, with gravity being so much stronger, we stay on the Earth, all the oceans stay on the Earth, and nothing flies off, and everything, the lakes are calm, and everything is very calm because gravity is 250 times or more stronger than these rotational forces. So it's just fascinating to me, and I hope you enjoyed this video. Do like it and leave some comments. I'm always learning great things from you guys. And do subscribe to my channel if you haven't yet. I have many more videos coming. All right, well, have a great night.